Welcome to the DRP Konya. Today we are hosting Çağlar Uyanık from University of Wisconsin-Medicine, and he's going to give us a talk titled A Gentle Introduction to Dynamics of Group Actions. And we can start, I guess.
Teşekkürler da. Thanks to everyone for coming, and thanks to organizers for inviting me to be here. It's a pleasure. Today I'm going to give an introduction to dynamics of group actions. So dynamics is also one of those things that's not well represented in Turkey. So I will try to make this introduction very gentle and try to motivate my talk through examples. So maybe the first question is, so what's dynamics? So the unofficial definition is it's the study of long-term behavior of physical or geometric object that evolves in time. So when you think about physical object that evolves in time, there are two things that come to mind. One of them is the planets orbiting the sun, and the other one is water flowing through the pipe. So that's why when you hear the word dynamics, a lot of the times it happens in like astrophysics or applied physics or applied mathematics when you're talking about differential equations of fluid dynamics. Today, I'm not going to do that. I'm going to talk about dynamics in a pure mathematics sense, and I have no interest in applications. So I'm going to start out with an example of what I think of as the archetypical example of a dynamical system. So that's going to be the circle rotation. So I'm going to take the usual circle of radius 1. This has perimeter 2 pi. And I would like to assign a measure to the circle. It's the usual Lebesgue measure. So the usual Lebesgue measure, which is the length measure on the boundary, tells you that this perimeter is 2 pi. But I just want to normalize it to 2 pi so that the total measure is 1. So it's a probability measure. Okay. And then I want to have some sort of a moving object on this circle. That is to say, I want to fix a point and I want to rotate this point by fixing some rotation angle. Okay, let's say that you start out with the point 1, 0, and then you apply a rotation d theta, where theta is some angle between 0 and 1, 0 and 1 times 2 pi. So what does that point look like if you keep iterating this rotation again and again? For example, if you're rotating by some sort of a rational angle, I guess in this case the rational angle is actually pi over 3, pi over 6. It has a very simple dynamics. There are only finitely many orbits. So you start out with the angle 0, and then you go to pi over 6, and then 2 pi over 6, and then 3 pi over 6, etc. And there are 12 orbit points total. And then it doesn't matter how many times you iterate. If you iterate this rotation by 1 billion times, you will keep coming back to these 12 points again and again. Okay, so that's called a periodic orbit. And there is actually nothing special about the point 1, 0. So if you pick some other point instead of 1, 0, maybe you pick this point on the circle and start iterating, it's also going to have the same number of orbits. And if you pick some other point, that's also going to have same number of orbits. So all orbits of this dynamical system, I haven't defined what the dynamical system is, all orbits of this game are the same. They are all periodic and they have the same period, regardless of the point you start with. So this is a very special dynamical system. It has all the nice properties you could ask for. But what happens if you pick an irrational angle? So this is the irrational angle I picked, and actually feed that into TIXI, and then actually looked at the orbits. So if you again start out with the point 1, 0, and then let's say that now you rotate by square root of 137 divided by 360 angle. Okay, that's some irrational number. So this is what happens after 20 iteration. It looks pretty discrete. It looks like the periodic orbit. This is what happens after 35 iterations. It becomes irregular. At these points, there are two things close to each other. These things are spaced out. And then if you do 60 times, it's becoming more irregular. And then if you do 150 times, it almost fills up the circle. And if you do 600 times, it's basically all over the space. Okay, so what it does, obviously, you can't fill up an uncountable set with 600 things. So there is an issue here because I'm giving the dots some fatness. So usually it doesn't have a fatness, but there are lots of dots that starts to fill up the entire circle. It becomes denser and denser as you go further and further iterations. And eventually it becomes equidistributed. So equidistributed is a technical term that means the following. It becomes denser and denser. So that part is covered. But not only it becomes denser and denser, it doesn't favor any part of the circle over any other part. So if you look at the orbit points, and if you pick your favorite region on your circle, and if you look at the proportion of orbit points that is falling into this your favorite region, it's going to be proportional to the length of the region. Okay, so that means if I pick a segment of length 1/4 over here, let's say this length is 1/4, and if I pick another segment of length 1/4 over here, and if I go up to, let's say, 10 to the 1500 iteration and look at the number of orbit points that falls into both of these things, okay, it's going to be roughly the same. It's going to be equal in the limit, but if you do very high iterations, it's going to be roughly the same. So that's what equidistributed means. It means that not only it becomes denser and denser, it doesn't favor any part of the circle over any other part. Okay, that's what equidistribution is. So this is sort of a nice dynamical property that shows up in number theory a lot. There are a lot of people who are studying the properties of prime numbers care about equidistribution properties. And it also shows up a lot in geometry and topology. But I'll come to that later on. Okay, so this circle rotation is actually the orbits are equidistributed if the angle is irrational. And it's a theorem of Weil from 1909 that it's actually equidistributed on the circle if and only if theta is irrational. Okay, so maybe this full generality of the theorem requires some real analysis, but you can prove the following two things. Here's some exercises for the undergrads. First, you prove that if the angle is rational, if theta is rational, means that it's something like P over Q times 2 pi, then it has a periodic orbit. You can actually figure out what the period of this orbit is. And two, if theta is irrational, in the sense that it's an irrational multiple of 2 pi, then the orbit is dense. This is really some sort of epigenol principle. It doesn't require lots of real analysis. But those are the two exercises you should work on in your free time. Okay, so this is a classical theorem of Weil that says that completely characterizes the orbits of circle rotation based on the angle. Okay, now that I gave a motivating example, or like what I think of as one of the first examples as a dynamical system, so let's actually go back and try to give a formal definition. So what's dynamics about? Dynamics is about dynamical systems. So you have some sort of a set X and a transformation T from X to itself. So that's a dynamical system. Without any identifiers on X and T, this is super vague and it could be anything. So you would like to perhaps say some things about this X and T. For example, maybe you want to say that X is a metric space and T is a continuous transformation, or X is a measurable space and T is a measure preserving transformation, or maybe X is a manifold and T is a flow on this manifold. So the more assumptions you put on this X, the more information you will get about the X itself by using the dynamical system. Okay, so the example I gave at the beginning is a classical example of a measure preserving dynamical system. So so a measure preserving dynamical system is a quadruple where you have a set, you have a sigma algebra on it, you have a measure and a measure preserving transformation. So a lot of times we are dealing with finite measures, and by normalizing we can mostly focus on probability measures. And a measure preserving dynamical system is exactly what this is. So you have a transformation that preserves the measure. So with measures, it's always the inverse because that makes things work better. The measure of the inverse image of a measurable set is the same measure as the original set. Okay, so the example I gave at the beginning, the circle rotation with the normalized Lebesgue measure is one of them. So you have the usual Borel sigma algebra of open sets on the circle, and your measure is the normalized Lebesgue measure, and your transformation is the rotation. So in general, if somebody gives you a measure preserving dynamical system or any other dynamical system on a highly specialized set with some extra structure, what you want to do is to understand the orbits. And that's what we did actually on the circle example. So we wanted to understand what happens to the orbits if you orbit means that it's the set of all tx, t squared x, t cube x, and so far for increasing powers of t, yeah. Right. In the circle case, every point has sort of the same behavior. Once you fix your dynamical system, once you fix your rotation, then either every point has a periodic orbit or everything is equidistributed. It becomes denser and denser. That's not always the case. So depending on the dynamical system, some orbits could have different behavior. And there are two types of behavior that we like from the point of view of maybe algebra and geometry. So a lot of the times, so dynamics is a field on its own, but a lot of the people who do dynamics do it because they want to get information about the geometry of an object or topology of an object, or maybe even algebraic structures of subgroups for groups acting on certain spaces. And two types of behavior are useful for proving theorems. One of them is the chaotic behavior. For example, the equidistribution example we saw earlier is one of those things. And there are various generalizations and variations on equidistribution. There's something called ergodicity, weak mixing, strong mixing, etc. There's a ton of notions that tells you that your dynamical system is really chaotic. It's like really mixing. You should maybe think of like weak mixing or strong mixing as you have some sort of a fluid and you want to put some paint in it, and then you try to mix it up. And if you're mixing it so well, everything will be the same. Everything will get the same paint. Okay. If you are not mixing so well, if only one part of the paint, if one part of the liquid is getting painted by the paint you put in, then it's not so mixing anymore. So the definitions are kind of natural. If it is mixing, it is mixing. Obviously, that's not an obvious formal definition, but that's what the chaotic behavior is. Okay. And there's another type of exciting behavior of these dynamical systems. It's the long-term stability. I'm going to give just one example of this. This is called north-south dynamics. So I'm actually going to write down an example with north-south dynamics. And turns out that this north-south dynamics is extremely useful for algebra. For example, in the study of linear groups, SL and R, or actually any linear group, or the study of mapping class groups of surfaces. And maybe automorphisms of free groups. This sort of behavior is responsible for lots of big theorems. Okay, so maybe I want to define ergodicity because it's such a central notion in dynamics. And then maybe go on to examples with north-south dynamics. Okay, so what's ergodic? Again, you have a measure-preserving dynamical system, and this T is called ergodic if T inverse of A equals A implies that A is a trivial set in the sense of measures. That means the only invariant sets are measure 0 or measure 1. There is no invariant set which is not measure 0 or 1. So that means your dynamical system, if you have an invariant piece, you can restrict to the smaller dynamical system by just looking at the invariant piece. So ergodic means, in some sense, that you can't cut open your dynamical system into two pieces. So it's sort of really complicated, and it doesn't have a decomposition. Okay. There are other ways of defining ergodicity, but I'm not going to do that. I'm just going to give you an example. The irrational rotation is ergodic. Okay, so that again requires some real analysis, but you can prove that rational rotations are not ergodic. So here's an exercise. Prove by finding an invariant set which is non-trivial invariant set that rational rotations are not ergodic. Okay. So that set is going to depend on the order of the rotation. Start with easy, start with order 2, start with rotation by pi over 2, and then try to exhibit a set on the circle which goes to itself, but doesn't have measure 0 or measure 1. Okay. So that's a nice exercise. Proving that irrational rotations is ergodic requires more work. Okay, so what's good about ergodic transformations is the Birkhoff's ergodic theorem that's almost 100 years old. It has this complicated looking formula, but what it says is that if you sample a function, so this is a function, this is some nice L1 function, along the orbits of your point, and if you average it, so there are n orbits, n orbit points, and if you sample your function along these orbits and average by n, it converges to the value of the function. Okay, so in informal terms, this is what they call time average converges to the space average. Okay, so instead of trying to compute this integral, for example, what you could do is you could find the value of the function at 10,000 points and then take the average. Okay. So by looking, so since this transformation is sort of super mixing and chaotic, you can read the entire information from the orbits of this dynamical system. That's what ergodic means. Okay, so for example, if you want to show that the orbit of an irrational rotation is equidistributed, you can use the Birkhoff ergodic theorem. So in the case you have the circle, so T is the rotation. So this is the rotation by irrational angle. And if you pick f to be the indicator function, the characteristic function of a set, so pick your favorite set here. And equidistribution meant that the orbits of this transformation, so this characteristic function gives you 1 if you're in the set and 0 if you're not in the set. So it measures how many times these orbits will fall into this region. Okay, so what this measures is that the proportion of orbit points that falls into this region. Okay. And that's just going to be the length of that, because the integral of the indicator function is just the length. So it says for almost every x, but you can actually turn it into every x using the properties of the rotation. Okay, so that's the one-dimensional example, which is the archetypical example of a dynamical system. And now I'm going to give you an example that comes from linear algebra. So 2, 1, 1, 1 is the best matrix out there. So if you look at all the matrices of all sizes, 2, 1, 1, 1 is truly the best. Like, there is no discussion about it. So I'm going to tell you why it's the best matrix out there. Okay, so because it has lots of nice dynamical properties, has connections to geometry, algebra, and all that. Okay, so what's good about this matrix is that it has 2 eigenvalues and 2 eigenvectors. So one of the eigenvectors look like this V plus, and the other one is V minus. So this blue one has an eigenvalue which is greater than 1. That's 2, 6, 1, 8. And the red one has an eigenvalue which is less than 1. Actually, these 2 numbers are 1 over each other. Okay, so they're 1 over each other. Maybe it's not. Maybe it is. It is 1 over each other because it's a determinant wall matrix. Yes, they're 1 over each other. Okay, so what that means is that if you apply this matrix to R2, this guy is going to get multiplied by a factor of 2.6 and get big like this. And this guy is going to get multiplied by a factor of 0.38 and get smaller. And if you apply multiple times, this gets really long in that direction, and this gets really short in that direction. Okay, well, that's great. But what happens to other vectors under iteration? And that's where we will see an example of north-south dynamics. Okay, we know what happens to V plus and V minus. And let's pick another vector, something like this. Okay, you can go to your favorite mathematical computing software, Wolfram Alpha or Sage, and actually look at what it does. What it does is that under iteration of ones, this V vector goes to AV, and then it goes to A squared V, and it gets closer and closer to V plus in the direction of V plus. Obviously, its length gets bigger. R2 is not a compact space, so we need to make sense of what convergence means, convergence of vectors means. But any vector that's not this one will converge to this direction under iteration of A. So if you take any vector, maybe something like this, it's going to get closer and closer to this one. Maybe if the vector is here, maybe it's going to get closer to this direction, but it is still going to get close to this line under iteration. So that's what north-south dynamics is. So in order to make this notion precise, so what does it mean to converge? So you can look at the projective space. So this is R2 minus the origin, where you identify 2 vectors if they are scalar multiples of each other. Okay, you can think of this as the quotient of the circle by the antipodal map, or you can think of the projective space. Okay, so what this does is it just records the direction of the non-zero vector, and it doesn't care about positive or negative. Okay, and if you iterate any vector which is not V plus under A inverse, if you look at A to the negative K, of any vector which is not v plus, then this is going to converge to v minus. Okay, converge in the sense that if you normalize so that the length of these things are 1, they will be the same in the limit. Okay, so that's an example of north-south dynamics. So there are two fixed points, v plus, or rather the equivalence class of v plus and v minus. And then everything else, which is not v plus and v minus, are going to converge to v plus under forward iteration and converge to v minus under backward iteration. Okay, so that's just linear algebra. Like, how do you show that these things converge? Well, you decompose this matrix as sum of two projection matrices, and then actually see that that's what it does. Okay, so what's this? What makes this example special is that this matrix is a 2-1-1 matrix, is an element of SL2Z. So it gives you a geometric context for this north-south dynamics. So you can now think of the torus, which is you can think of as the quotient of the R2 by the integer grid. That means you identify every point which differ by an integer vector. Okay, but there you can only choose one fundamental domain at the origin, and you can just think of this as the square where the opposite sides identified. Okay, so when you identify opposite sides, when you do the first identification, you get a cylinder, and then when you do the second identification, you get a torus. Okay, so this is the surface of a simit or a bagel, okay, or a donut. Okay, so this map, since it preserves this map system, it preserves the integer lattice, it actually gives you a well-defined map on the torus itself. Okay, so for example, I will just show it for the ones. When you iterate this torus, but apply this map to the torus, you get something like this. But then you can cut it along these lines and then glue it back here like this. Okay, and then you can cut it along these lines and then get the original torus back. So these colors over here are supposed to indicate what happens to the inside of the torus. So it's making some non-trivial change inside of the torus. For example, this, whatever that color is, brown region is split into two pieces, and this blue region is split into two pieces as well. Okay, and you can imagine that if you keep doing this, this region is going to get all mixed up. It's going to go all over the place. So is there a question in the chat? Pink. Thanks. Thanks, Karen. It's not pink, but that's okay. Yavraz. I don't know what the English word for that is. Okay, so what's the long-term behavior of this map on the torus? It has exactly one fixed point. It's the corners of this square that are identified. Well, that's what it says. And almost every point with respect to the Lebesgue measure. So you can think of this as a subset of R2, and it naturally admits the area measure from R2, which is the Lebesgue measure. And with respect to this Lebesgue measure, almost every point equidistributes. So almost every point means that a full measure subset of the points inside of the square equidistributes under the iteration. So that means if you pick a point with probability 1, and if you look at its orbit under applying this map, it's going to go all over the place. It's going to become denser and denser, and it's not going to favor any part of the torus over any other part. Okay, so you can actually create a conjecture. So you can think which points. So what is the maybe algebraic conditions on the coordinates of this point so that it equidistributes? Okay, So this map is actually a super famous map. I'm not a fan of it because I discovered it. It's called Arnold's cat map. So if you actually Google Arnold's cat map, it gives you images of cats, and I like cats. But the property of this is that most of the points with rational coordinates will get near itself under, I think, 600 iterations or something. So if you have a pixelated image where all the pixels are located at rational points, after 600 times, the picture of a cat comes back to itself. Okay, so this is an example of what people call an anosov diffeomorphism. So turns out, if you want to understand the maps of the torus, there are three types. The two types are, one of them is a shear, the other one is a finite order map, and the other type is a hyperbolic type of map. And those fall into anosov diffeomorphisms, and they are the generic type of diffeomorphisms of the torus. And they carry the most information, they have the most chaotic behavior, and they are the most useful ones. Turns out this Arnold's cat map, an anosov diffeomorphism, led to a whole area of mathematics, which is the study of hyperbolic two manifolds and their homeomorphisms and their mapping class groups. So in the 70s and 80s, Thurston generalized this anosov diffeomorphisms to high genus surfaces, meaning that surfaces with multiple poles, not the torus. But there is no longer an anosov map, but there is a pseudo-anosov map, and use this to say something about geometry of three manifolds. Okay, I'm not going to get into that, but I just want to sort of justify the reason why I think this is the best matrix in the world, because it leads to so many different things. Okay, so speaking of the torus, what does this north-south dynamics of the linear map tell you about the geometry of the surfaces? So in the study of surfaces, there is this usual saying that if you want to understand surfaces, you should understand curves on surfaces. So if you want to understand the high dimensional object, you should understand the smaller dimensional objects that make up the surface. Again, in this case, we have the square and the opposite sides are identified, and that gives you a torus. And for example, you can think of this vector 0, 1 on the square, which descends to this meridional curve on the torus. Okay, if I apply 2, 1, 1, 1 to this torus, that induces a map on here. So 2, 1, 1, 1 induces a map on here. And what does this curve look like under iterations? Okay, I think this is the curve 1, 1, not 0, 1. And then if you apply the matrix 2, 1, 1, 1, this is the image of the curve. So in the square picture, not on the torus picture, but in the torus picture, if the curve is, maybe if you're going once and twice in the horizontal direction and once in the vertical direction, you go twice in the horizontal direction here and once in the vertical direction here. Okay, so there is a unique curve up to homotopy for each integer vector. So the curves on these surfaces correspond to integer vectors on this lattice. Okay, if you apply this map, what happens is actually that curves get longer. It winds around both the meridian and longitude multiple times. It gets longer and longer as you iterate, and longer. And then this is actually the straight line segment in the direction of V plus. Remember, V plus was some vector which had irrational coordinates. So it actually never closes up. So if you hit a curve on your torus in an irrational slope, it just keeps going. But any other curve under sufficiently many iterations becomes really close to this irrational direction. Okay, so if you take any curve, doesn't matter which curve it is, a closed curve, and if you apply the matrix 2, 1, 1, 1, eventually it becomes more and more parallel to this irrational direction. And this is independent of the curve you started with. And same thing happens for backward iterates. So if you pick any curve and apply the matrix A to the negative n, everything is going to converge to the direction of V minus. So in particular, no curve has a periodic orbit. So this map 2111 has some sort of an exponential growth on curves. So no curve ever comes back to itself. So if you have seen surface topology before, there's a map called Dane twist, which is taking a curve and cutting it along that curve, twisting by 360 degrees, then gluing it back. So for example, that curve is fixed. That's also a homeomorphism, but it has a fixed orbit. So this is very much not like a Dane twist. It's an extremely complicated homeomorphism of the surface. And it's one of the prime examples of north-south dynamics and equidistribution in a single dynamical system. So it turns out this north-south dynamics has applications to what's known as Tits alternative. So Tits was a French mathematician who proved his alternative for linear groups. And many other people proved this alternative for other groups that are important in low-dimensional topology. Okay, so where do these dynamical systems on the torus actually show up? So it shows up in the following setting. So this is the setting of rational billiards. Many of you probably saw what a billiard table is. It's a table. A lot of the times, your table is just a rectangle. But if you want to mix things up and make it mathematically interesting, you can make your table kind of crazy. It follows the basic rules, not just in real world. It's the frictionless table, and when you hit a side, you're going to have the reflection angle be the same as the angle of incidence. Okay. And your ball is a point mass, so it's not a big ball, and it keeps going as long as it hits the sides. Okay. So this is obviously a mathematical example, but it came from physics. So people wanted to study the orbits of these billiard trajectories on various types of rectangular billiards. So for the square, again, this is very easy to understand. Let's say that for simplicity, you start from here, okay? And then you can ask, okay, I'm going to shoot a billiard in this way with this angle theta, okay? When does it ever come back to one of these vertices? Okay, so does it hit any vertex? Okay, so that's something you should think about. And it has something to do with the irrational rotation. But originally, this was again introduced by toy models for some physical phenomena. So physicists would like to understand if you release some gas inside of a room, and what happens to these gas molecules if they are jumping around, hitting the walls. Okay, so obviously they are more interested in three-dimensional rooms, but let's just try to understand two-dimensional example first. So if you have some gas molecules, and obviously in real world, gas molecules don't behave like they're not going to have this two angles equal to each other. But let's just make everything perfect and try to understand the simplest case, and maybe we can say about something physical if we understand the simplest case. And that introduced this notion of billiards, also mathematical curiosity. Oops. And it also has connections to illumination problem. I'm not trying to give a subtle message about illumination, but it's sort of an important property in dynamics. So if you have a dark room and you want to put a light source inside of a dark room and want to illuminate the entire room, Okay, for a square table, that's really easy. It doesn't matter where you put the light source, it's going to illuminate every other point. Okay, so you want to use the minimal number of light bulbs to illuminate that room. But for a room like this, again, I'm assuming that the room has mirrors all over the place, so that if I put a light source here and it's going to maybe bounce off here so that it's going to illuminate this point, for example. But can you guarantee that every point in this room is illuminated by a light source that I put here? Okay. So that turns out to be a difficult problem. It's not so difficult when the angles of these things are all rational multiples of pi. But in general, if somebody gives you a strange room, maybe it looks like this, and then you can ask, well, I'm going to put a light source here. Does it illuminate the entire room? That turns out to be a very difficult problem. And it has connections to moduli spaces of translation surfaces. Although it's very easy to state, it has connections to really deep mathematics. Anyways, so the billiard problems, or the trajectories of balls inside of billiards, both have physical applications. Like the gas chamber also have this interesting illumination problem. Oops, that's what I said. Okay, so I put those lights. And can you illuminate this point by that point? Okay, I did all of that in one slide. Okay, so it turns out understanding these billiard paths is difficult because if you want to understand, let's say I want to understand this path that starts off from here, and then once it hits a wall, it bounces off, and then it bounces off like this, bounces off like this, and so on. So all that bouncing off and changing directions is kind of hard to keep track, right? Especially if you want to understand the long-term behavior until, let's say, 1 millionth time, it's going to be lots of changing directions and bouncing off. Okay, so recording this data is going to be painful. So what Katok realized, I think it's attributed to Katok, but I'm not sure, this unfolding procedure. It says, well, don't do that. Instead of bouncing off the table wall, you just reflect your table along that edge. For example, when I hit this edge, instead of bouncing off, I'm going to reflect this table while keeping track of which edge is edge. So this L over here indicates that. So if I have the L letter like that, and if I reflect that table, that L is going to look like this. And then once I hit another wall, instead of bouncing off like this, I'm going to just reflect the table and then keep track of what the table goes to, and then do the same thing. But eventually, after finitely many reflections, if it is a rational polygon, you're going to come back to the same position, and it's just carried along here. So that means instead of trying to keep track of this complicated billiard trajectory, you can keep track of the straight line trajectory on a possibly bigger polygon with some side identifications. So the original rectangle, a billiard table on a rectangle or a square, actually gave me some sort of a straight line trajectory on the torus. So but it's a 2x2 torus, but that's fine. So keeping track of straight lines is way easier than keeping track of lots of parallel lines. Okay, so torus is an example of a translation surface. So what's a translation surface? It has this definition. It's just like a manifold, where Alp said Katok Zemlyakov. I think Alp was a student at PSU. I never met him, but if he says so, he's probably right. So this definition is sort of difficult to work with. It's like a manifold definition. This definition is also difficult to work with. It uses fancy words like holomorphic one form. Who knows what that is? But this last definition is the best one. It's just bunch of polygons. So a translation surface is bunch of polygons on the plane where the parallel sides are identified by Euclidean translations. Like the torus example, where you have a polygon where each side is identified by a translation. We already saw an example, which is the torus, and there's also the octagon. When you glue the opposite side of an octagon, you get a genus 2 surface. But one thing you need to realize is that this is topologically a genus 2 surface, but it's not Euclidean everywhere. So the torus is Euclidean everywhere. So if you pick any point, around that point, the total angle is 2 pi. For the octagon, it's going to be slightly different. I'll come to that. And we say that two translation surfaces are equivalent if there's an orientation preserving isometry, preserving the given preferred direction. In other words, two translation surfaces are equivalent if in the polygonal representation, you can just cut and paste and get the other one. Okay, so that's the equivalence. So this definition is super nice. You're just working with polygons, but turns out that it's also equal to these two other definitions that that are important in Teichmüller dynamics and some fancy mathematics. And the translation surfaces are sort of stratified or classified by the number of singularities and excess angle at each singularity. So as I said, the torus has no singularity. At every point, the total angle is 2 pi, because at each of these points, you just have pi and pi adds up to 2 pi. Only problem could possibly occur at this vertex, but total angle is 2 pi there too. One more question. Oh, somebody asked, how do we do unfolding when the billiard table is not square and of some other weird shape? Yeah, so you do in the exact same way. So if you hit an angle, you just reflect on that h, and the assumption that the angles are rational makes sure that after finitely many steps, you actually get the same copy and you can glue it back. So that's a good exercise to check. So you can always get a surface if the angles are rational, and maybe see Hubert-Schmidt for this. Yeah, that's a good exercise to check. For the octagon, you have one singular angle, so everything else just glues up to the locally Euclidean shape, except that one angle. You have 3 pi over 4 for each of these vertices, and if you glue 8 of them, the total angle is 6 pi. So you get this surface which looks like locally Euclidean everywhere, except at a point where the total angle is 6 pi. It's like lots of sectors coming together to form a total angle 6 pi. Okay, so if you know some topology, genus 2 surfaces are negatively curved, so they can't admit any flat surfaces. So you can think of this 6 pi as all of the curvature is concentrated at that point. All of the negative curvature is concentrated at that point. And we can record this by just a vector, which is the number of singularities and the excess angle at each thing. And using again some geometry, the Poincare-Hopf theorem, you can actually deduce what the topology of your surface is. So in the octagon case, I told you that the resulting surface is genus 2, and you can actually compute this by using the Poincare-Hopf theorem. Okay. You can put these things into spaces. These are called moduli spaces or strata, according to their topological type. The torus lies in H empty set because there is no singularity, and the octagon lies in H2. there is one singularity of axis angle 2 pi plus 2 times 2 pi. And the decagon, again, it's a genus 2 surface with 2 singular points where both of them has 4 pi, 4 pi. Okay, so why am I telling you this? Because of the dynamical model I'm going to tell you right now. So this is attributed to this person. I don't know how to say his name. Plow in the parameter space and harvest in the phase space. So what that means is that if you want to understand a dynamics on an object, what you could do is you could vary the object in the moduli spaces of objects. For example, if you want to understand the dynamics on the torus, instead of trying to understand what's happening inside the torus, maybe you should deform the torus and understand the dynamics in the space of all tori. For example, if you deform your torus by a little bit and get some sort of a parallelogram, the resulting surface is again a torus. So it turns out these things fit into a moduli space called the Teichmüller space. And turns out understanding the dynamics inside of an object using the dynamics in the moduli space of an object is incredibly helpful. So, for example, this is what Maryam Mirzakhani did in her PhD thesis, which was part of the reason she got a Fields Medal. So in order to understand the dynamics inside of surfaces, she understood the dynamics in the moduli spaces of surfaces, and then used those things to say meaningful things about curves on surfaces. Okay. And how do you move in the moduli space of surfaces? There's a nice way of moving by applying the SL2R action. So the transition surfaces are just polygons. So if somebody gives, and you can write that polygon as a subset in R2. And if somebody gives you a matrix in SL2R, so this is an invertible matrix of size 2 by 2, you can just apply this matrix to this shape and get something like maybe this. Okay. And if you started out with a torus like this, and if you apply a matrix, you get another torus. Well, it's not the same torus, but it's a torus with different shape. Okay, so using this action, you can move in the space of moduli space of transition surfaces.
Is this action preserves the area?
It preserves what?
The area, the measure.
Yes, because it's SL2, not GL2, it preserves the area. Yeah, that's a good question. Yeah, if it was GL2, then it wouldn't preserve the area, but SL2, that's area preserving. Yeah. It's the example I gave earlier. It's 2, 1, 1, 1 matrix. It takes this torus to something else. And it preserves the unit area transition surfaces, just like Krusha does, because it's in SL2R. And there's various types of subgroups of SL2R, one parameter subgroups of SL2R that one would really like to understand. One of them is the rotation, so that's sort of easy to understand. If you have a surface, you just rotate it. The other one is known as the geodesic flow, which is stretching in one direction and contracting in another direction. It's called the geodesic flow because turns out that the orbits of these things are geodesics in moduli spaces. And this is called the horocycle flow because the orbits are horocycles in Teichmüller space, which is isomorphic to the hyperbolic plane. Doesn't matter so much. Okay, so right. So what's the goal? The goal is to use dynamics to say things about the objects or the geometry of the objects. So maybe I'm gonna tell you one number theory problem, and then tell you how dynamics come into play. So you can look at all the primitive integers inside of Z2. Okay, so primitive integers, you can think of them as you stand in your R2 and then you are a person based at the origin, okay? And then think of the integer points as trees. Ooh, that's a terrible way of doing things. Let's say that you have a tree at each of the integer point in R2, okay? Maybe I'm going to draw one more. And the primitive integers are the ones that you can see from the origin, okay? So for example, if you're a person looking at in a two-dimensional space, you can see this point. So that's a primitive integer. That's 1, 0, okay? But 2, 0 is not, because you can't see that. That's blocked by this one, okay? Again, 1, 1 is a primitive integer because you can see it. But 2, 2 is not a primitive integer, okay? Similarly, this one is a primitive integer, but this one is not, okay? So you look at all the trees that you can see from the origin. Let's say I fix the origin, and you can look at all the trees. Can you give an algebraic characterization of these things? Any suggestions?
Well, if the greatest common divisor of the coordinates of a point is 1,
Yeah.
then that should be a primitive integer.
Yeah, so the primitive integers are the ones where the coordinates are relatively prime, okay? So if the coordinates are relatively prime, then you can actually see them through the origin. So these are primitive integers. We know a lot about these primitive integers, we can actually count them. So for example, if somebody gives you bigger and bigger balls of radius r, okay, and you can ask how many primitive integers are in the radius r, or maybe you would like to work with squares. There is approximately 2r times 2r total integers, and how many of these are primitive? Okay, so that's known as the Gauss circle problem, and it has something to do with the Riemann zeta function, the proportion of the primitive integers. And actually, if you draw these lines through primitive integers in your R2, and you look at what these lines intersect in the unit circle. So you draw longer and longer lines for primitive integers where the size is getting bigger and bigger. Okay, obviously there's infinitely many of them, so there's not just finitely many, but if you do bigger and bigger radii, you're going to see that the directions of these primitive integers also equidistribute. Okay, so that means these directions appear randomly on R2. Okay, so directions equidistribute. So one question you can ask is this a random process? So is this a random process? So random process is actually a technical term. Is this a Poisson distribution? So there's some sort of a notion of Poisson distribution in probability, which basically means the following. Let's just focus on the ones that are between x equals y and x equals 0, and all these slopes are between 0 and 1. Okay, so Poisson distribution would be something like this. You pick a dart and try to hit a point in between 0 and 1. So if you close your eyes and if you try to replicate this process multiple times, that should give you a Poisson distribution. So okay, it's truly random, what probability people would call. And the question is, do these things appear truly randomly? Okay, and turns out the answer is no. And turns out the answer can be given using dynamics on moduli spaces, these which are quotients of SL2R by SL2Z. So that's sort of an incredible thing. So there is this simple question about prime numbers, and you can easily generate all these primitive integer vectors inside the Z2, and you can ask, do these things appear randomly? Well, that's just a question about prime numbers. What does it have to do with dynamics on SL2R modulo SL2Z? So the answer is you can look at the paper by Atreya and Chung, and you can look at the paper by myself and my collaborator work, and I also have a paper with my students that explores these type of questions. So trying to understand the randomness on surfaces using dynamics on moduli spaces. Okay, I'll stop here.